And we're back. So we've talked about the background to redox reactions. Which ones are they? So like combustion reactions, the formation of ionic compounds, those kinds of things. Now we're actually going to start getting into defining oxidants and reductants and looking at simple half equations. A word on this, as I said, we do use a lot of very similar sounding words in this unit, so make sure you're keeping a good vocabulary list and don't get confused. Okay, in this video we're going to cover the terms oxidant and reductant. We're going to identify the oxidant and reductant in a reaction, write simple half equations, identify them as either showing oxidation or reduction, and then write a complex redox equation for a simple redox process, so joining them together. Let's get started. You may remember back to a reaction you did in term 1 when we were looking at imperial formulas and molecular formulas of the formation of magnesium oxide. You would have taken magnesium ribbon and then burnt it in a crucible, and before you did that you would have scrubbed away at the oxide layer that formed on the outside. The burning of the magnesium ribbon is actually a redox reaction. We know this because it forms an ionic compound. Okay, so from elemental forms, so we know that they have either transferred or gained their electrons. So the oxidation reaction occurs simultaneously, so that the overall reaction for the burning of the magnesium is given by this equation. We know that 2 magnesium solid reacted with oxygen gas to form 2 MgO. We know this because we can say that the magnesium is a group 2 metal, so when it forms ions it'll be +2, and oxygen, when it forms ions, it's a non-metal, so it's going to gain electrons, so they'll be -2. And if we look at this formula, MgO, they balance out and it's a neutral ionic compound. So we know in this case that an electron transfer has been formed because we have a new bond formed between a metal and a non-metal. What's happening is the magnesium, each magnesium is giving up 2 electrons to each oxygen to form the ionic bond. Okay, so if we remember back to the fact that we said that oxidation is loss of electrons, then the magnesium is losing electrons. Okay, it's losing 2 electrons, and the oxygen is gaining them. Okay, so it's becoming more negative, because when we gain electrons, we become more negative. So if oxidation is loss and reduction is gain, then we can say that during this electron transfer, the magnesium is oxidized. That is, it is undergoing oxidation. And the oxygen is reduced, okay, because it has gained electrons. It is undergoing reduction. Okay, so the magnesium is oxidized. Because it is oxidized, it is giving away its electrons, so the process it is causing to occur, to happen, is reduction. Okay, so the magnesium is forcing its electrons onto the oxygen, so it is causing the oxygen to be reduced. So magnesium, in this case, is going to be known as the reductant, and the reductant is oxidized during the redox process. The oxygen is accepting those electrons, so it is facilitating the oxidation, so it is the oxidant, and in the process of facilitating the oxidation, it is reduced. As I said, this terminology is going to get a little bit confusing. So if we split the reaction up into what's happening for the oxidation process and the reduction process, we can actually see what's happening to the electrons. In the case of the oxidation process, remembering that oxidation is loss of electrons, magnesium goes from magnesium solid to magnesium 2+, okay, and gives up 2 electrons. This is the oxidation. The reduction process, oxygen is gaining 4 electrons, because remember there was 2 lots of magnesium, and in order to get 2 O2 minus, we need to have 4 electrons here. We can see that it's gaining electrons, so the electrons are on the reactant side, and it produces 2 lots of the oxide ion. Therefore, it's gained, so its reduction is gain, and it is the reduction process. Okay, you can, as I said, I use oil rig. You can use Euler and Rigel in order to help you remember that in an oxidation process, the electrons are produced, so they end up on the right-hand side, which is our product side. Okay, and in the reduction, the electrons are used. They're getting put into the compound, so they're being gained. So electrons are used, so they are on the left-hand side because they're on the reactant side. They're being used up. So as we talked about before with magnesium and oxygen, the magnesium is the electron donor, much like an acid is a proton donor. The magnesium is the electron donor, so it allows or facilitates the oxygen to be reduced, so it is known as a reducing agent or a reductant. Okay, agents facilitate things to happen, and in this case, because magnesium is giving up its electrons, it is facilitating the reduction of the oxygen. So the reductants always undergo oxidation, okay, and the oxidants undergo reduction. The electron acceptor, okay, is the oxidizing agent because it is allowing oxidation to occur, so it will be reduced in the process. And just as we had with acids and bases, we can get conjugate pairs. We can see here that the Mg2 plus and the O2 minus are what we refer to as conjugate redox pairs. Okay, they're showing us the 2 parts of what has occurred. Okay, and when we come to writing half equations, i.e. the 2 equations, one that shows oxidation and one that shows a reduction, we want to pull out the conjugate redox pairs from an equation. So when we write overall redox equations, the oxidation and reduction reactions are represented as a sum of 2 half equations, one for oxidation and one for reduction, using conjugate redox pairs. Okay. Then from that, once we have the 2 half equations, and we need to balance our charges on here. Okay. Once we have that, we can add the 2 half equations together to determine the overall redox equation. And then we need to make sure that the number of electrons lost in the oxidation reaction must be the same as the electrons gained in the reduction reaction. Because remember, oxidation and reduction happen simultaneously. They can't happen independently. So we need to make sure that any electrons that are given off are accepted by something as well. Key thing to remember is that we've talked about the conservation of mass and the conservation of energy. When we're talking about writing chemical equations that show redox, we also need to consider the conservation of charge. In both half equations and overall equations for redox reactions, we need to watch the number of atoms of each element is balanced as always, because atoms are conserved. But we also need to make sure that the total charge on the product side is equal to the total charge on the reactant side. We can't have electrons just floating around on their own. That just doesn't happen. Okay, so when half equations are added together, we must never have an excess of electrons. Never. We only have the electrons there to help us balance the equation. In the full balanced equation, there should be no electrons present in the equation. So let's have an example of writing some half equations. If we look at the following reaction, where we place zinc metal into a solution of copper 3 nitrate and leave it overnight, we will see the blue color of the copper solution diminishing, indicating that the concentration of copper is decreasing. Okay, and we will start to see a deposit of a dark reddish copper metal on the zinc surface. So overnight, okay, we will see the formation of copper metal and the color changing in the solution. What we'll also see is that the zinc strip slowly dissolves away. Is this a redox reaction? Yes, because we can see that the charge on the copper is changing. Okay, so if we have a look, we can see that what's happening is we start with Zn solid and we are reacting it with copper nitrate, and overnight we are seeing the formation of zinc nitrate as a new product and copper solid. You may remember this as a displacement reaction because displacement reactions are redox reactions. So if we have a look at this, we can break it down into two halves. We can say that the zinc solid is going to Zn2+ because the nitrate is aqueous on both sides, so we're going to remove the spectator ions. Okay, nothing's happening to that nitrate, so we don't care what's going on. So we're going to remove the nitrate spectators. And we can see that zinc solid is going to Zn2+ aqueous, and copper solid, copper 2+, 3+ over this side, is going to copper solid. And if we have a look at this, it would be copper 2, so let's just fix up our charges, is going to copper solid. So now our atoms are balanced, okay, but we don't have charge being balanced. And the previous slide told us we had to balance our charges. The only thing we can balance charges with in redox reactions is electrons. So if I take my zinc solid and I look here, I've got zinc 2+. To go from 2+ to 0, because this is 0 on the left-hand side, I want it to be 0 on the right-hand side, I'm going to add 2 electrons, okay, because this is taking away this positive 2 by adding in a negative 2. In this case down below, I have copper solid down here and copper 2+ over here. So if I add in 2 electrons over here, I can now see that these are equal. If I go back to remembering that oxidation is loss of electrons and they will end up on the right-hand side, then I can identify this top reaction as an oxidation reaction. And reduction is gain of electrons. So my electrons will end up on the left-hand side. I can see that the copper is gaining electrons, so I can identify this as reduction. So the overall half equation for the oxidation reaction is zinc goes to zinc 2+ aqueous plus 2 electrons. The reduction equation is copper plus 2 electrons goes to copper solid. Okay, so in this case, we have an oxidation and reduction half equation. Okay, when we go to write the overall equation, we would just add the two together and the electrons would cancel out. So we would end up with zinc solid plus Cu2+ aqueous is going to form Cu solid plus Zn2+ aqueous. Again, this is a net ionic equation. We have ignored the nitrates because they're spectators. So what I want you to do is actually pause the video and work through the next few questions on your own. This will take you a little while, but it's important that you get practice on these, and we will look at these questions in class as well. So question 1, when a strip of nickel is placed in silver nitrate, the nickel dissolves and a silver deposit forms. So we know that this is going to be nickel aqueous. This is going to be Ag solid. And I started with AgNO3 aqueous. Okay, so it says write the half equations and an overall ionic equation for this reaction. Okay, so we've been told all the things that we had for our reactants. So I'm just going to write it from the description. Nickel solid is placed in a solution of silver nitrate. The nickel dissolves and a deposit of silver forms. This is from the description. Okay, my nitrate's always going to be aqueous, so I know that this is going to be a spectator ion and I can remove it, giving me the ionic equation. Okay, so now I'm going to pull out my two redox pairs. So nickel solid is going to nickel 2+ aqueous. So the charges to balance, so 2 electrons. My other redox pair is Ag plus going aqueous, going to Ag solid. Okay, I need an electron over here to balance it. But what I can see now is if I try and add these two together, I have an extra electron in the nickel side. So what we're going to do is we're going to multiply this equation by 2. Okay, so that will give me 2 electrons, 2 Ag plus gives me 2 silver solid, and then I'm going to add them together now that my electrons can cancel out on both sides. Sorry. Just seem to have started off something weird. There we go. Okay, so we're going to add these together now, where we end up with 2 Ag plus nickel solid is going to give us nickel 2 plus 2 Ag solid. And as we can see, they have cancelled out the electrons on both sides, and we now have a balanced ionic equation showing the redox process. Okay, so that's writing it for question 1. I'd like you to go on and try some of the other questions and then come back to see the solutions. Okay, so hopefully you were able to do question 2 for the formation of sodium chloride. And the 2 half equations are presented down here below, where sodium is being oxidized, going from sodium metal to sodium ions, and chlorine gas is being reduced, forming 2 chloride ions. Our next question provides you with 4, where you need to rewrite the equations as 2 half equations, and again and represent which is oxidation and which is reduction. So again, have a go at these and then come back to see the answers. Let's have a look at some of these answers. So hopefully you were able to come up with the 2 half equations by finding the redox pairs. Okay, and you will notice that this one here is, of course, our reaction of a metal with acid, which we stated wasn't a acid-base reaction. It's actually a redox reaction. So we have the oxidation process of the zinc forming zinc ions and the reduction process of the hydrogen ions forming hydrogen gas. Okay, in number B, the magnesium and oxygen is the same as the example we did earlier, where the magnesium is oxidized and the oxygen gas is reduced. For C, we have fluorine and nickel reacting together, forming nickel fluoride. So we have the formation of an ionic compound, which is going to be redox. The nickel has given up its electrons, so they're on the right-hand side, so it is oxidation. The fluorine has gained electrons, so they're on the left-hand side, it is reduction. In the case of D, we have copper ions reacting with iron 2 plus ions. Iron can have multiple charge states. It can be iron 2 plus or iron 3 plus. So in this case, the iron goes from iron 2 to iron 3, so it has been oxidized. Okay, and the copper goes from copper 2 to copper solid, so it has been reduced. Hopefully you got each of those correct. Another couple of questions for you to have a go at and then go through the solutions. Okay, so in this case, we have sodium metal being oxidized by atmospheric oxygen, and we're given the half equations. So we're asked to identify the half equation representing the oxidation reaction, remembering that oxidation is loss of electrons, so the electrons will turn up on the right-hand side, making our sodium half equation the oxidation half equation. And then balance the overall equation. Well, I have 4 electrons here for the oxygen. I have 1 electron here for the sodium. So we're going to have to multiply by 4 in order to get the charges to balance. So if we write the overall equation, we will now have 4 sodium. That will give me 4 electrons. They can cancel out. So I will get 4 sodium metal. Reacts with oxygen gas to produce 4Na plus 4Na plus hasn't given us states. Yes, okay, solid. Plus 2O2 minus solid. Okay, because this will come from the fact that sodium metal will react with oxygen gas to produce Na2O and 2 lots of it. Okay, so we can see here that 4 sodium is going to form 4Na plus, and O2 gas is going to form 2 lots of O2 minus. So that's it for this. I know this one's really long because we've got lots of practice equations, but hopefully you've had a bit of practice on the questions as well. You should be able to define the terms oxidant and reductant, identify oxidation and reduction reactions and write their half equations. Okay, be able to term these as either oxidation or reduction, and then write a complete redox equation for a simple redox process at this stage. And we'll have some more practice in class.